Okay, so a quick recap of what we've done in the previous three videos. We saw that when you look at a family, a blue family of triangles rigidly rotating about its symmedian point, the symmedian point of its inversive image with respect to this green inversion circle was stationary. Okay, and this is true for all positions of the inversion circle. We also saw that if instead of pivoting about x6, the symmedian, I was pivoting about the first isodynamic point for O sufficiently far away from the pivot point x15, the locus of the inversive first isodynamic was also a stationary point. And the same was true for x16. Let's go ahead and make O be sufficiently far. How do they do this? There you go, I think like so. Let's scale this out just to confirm that we can indeed get this kind of phenomenon for x16. Yeah, so if O is sufficiently, in this case, close to x16, pivoting x16, then the circumcircle of the blue family, let's draw that, is always safely away from the circle of inversion, the center of inversion, so that the second isodynamic of the red family, the inversive family, is always a point. So this is working for the symmedian, for the first isodynamic and the second isodynamic, and there's some more details that you can see in the previous video about what happens to the first and second isodynamic loci, which can contain both a point and a circular arc or two circular arcs, depending on the position of the center of inversion. So now let's look at a similar, to a set of phenomena similar to x15 and x16, but involving another point, x61, also on the Brocard axis. So all these points, the symmedian, first isodynamic, second isodynamic, and now x61 and x62, which we're going to cover in this video, they are points, they're special points on the Brocard axis, which have interesting phenomena with respect to this kind of a pivoting experiment. Okay, so now let's go to x61. So here's x61, and I'm going to move the center of inversion far enough to the right. There it is. And just so we can recap a little bit, what am I really doing? Again, I'm taking a triangle, some random triangle. It doesn't have to be this one, but I'm choosing this one, and I'm just making it rotate about a fixed triangle center, in this case x61, in the plane. Just for quick reference, it would be nice for us to actually see what x61 is, right? So let's go ahead and do that. Let's do that. F12. Let's go ahead and see using Kimberling's list what x61 is, just for completion here. So x61, Kimberling's list. This is called the isogonal conjugate of x15. And it has a bunch of interesting phenomena here. I haven't really pinned down what's going to cause the current set of phenomena to take place. Okay, but this one is a specific point. These two actually, x61 isogonal conjugate of x17, and x62 isogonal conjugate of x18. Even though x16 and x18 don't do anything, 61 and 62 do. So let's go back to our simulation. So it would be this one and that one. Okay, so here we got x61. We're going to make this triangle rotate about it. Okay, now let's light up the inversion circle. Let's light up the inversive family. Let's move this inversion circle a little bit to the left here. And you can see right away that we're getting the same phenomenon we got from with x6, x15, x16, in that x61 of the inversive family is a stationary point. Okay, now, is it always a stationary point? So how we're going to do this, we're going to start doing the same playing the same game. We're going to start moving O inward, the center of inversion inward, to a point where it can actually become interior to this moving family of circumcircles. These blue circumcircles, you can see now that the blue circumcircles are always passing clear from O. O is never interior, but if O is now brought a bit closer, like so, okay, and I can show that at some point when O is internal, now x61 is going to now, again, as we saw before, let's scale this up, contain two phases. It's going to contain a stationary phase when O is exterior and an arc-like phase when O is interior. Okay, so what's the arc-like phase? Let's look at it. So right now, O is interior to the circumcircle, center of inversion interior to the circumcircle. So x6 to the minus 1 is sliding along an arc. Now this arc turns out to be the arc of an ellipse. It's no longer the arc of a circle. Okay, and how do I know this? If I keep moving O inward, and it's a very similar phenomenon, okay, I start exaggerating this locus, so let's scale this down a bit. Let's move to the left, this to the left, and let's keep moving O to the right, to the left. At some point you get that self-intersection. You can see here that this this arc part here starts looking like the portion of an ellipse. Let's follow this motion. O is currently interior to the circumcircle, so x61 is following the arc of an ellipse. And when O jumps out of the circumcircle, x61 goes to this location here, and it's stationary, while O is outside of the circumcircle. So you have these two phases, either moving along the arc of something that looks like an ellipse. And how am I going to know this is an ellipse? I'm going to keep moving O to the left, and at some point I'm going to go through a transition. You see, I go through this transition now, and what this transition is actually marking is a certain position for the inversion center, close enough to the pivot x61, so that the circumcircle of the blue family always contains O. And when you do this, x61 now is stuck to this continuous curve. And what is this continuous curve? I can actually show what's being numerically calculated. This is saying, okay, this is a numerical ellipse up to precision. It's not a circle, as we saw with x15 and x16. It's actually an ellipse. And here's the aspect ratio of this ellipse. So I can keep moving my OX to the left, and this continues to be an ellipse when, of course, O is going to be identical to x61 if it's sufficiently to the left. This ellipse, you can see here that its aspect ratio is coming closer and closer to 1. So if I keep moving this guy inward towards 0, and when this thing is exactly equal to 0, I'm going to get that this elliptic path becomes a circle. So let me actually move on to this negative side. Not so much over here. So now O is to the left of x61. I'm again an ellipse. It's this thing, and I'm going to get sort of the mirror image of this phenomenon as I move OX to the left. Then you undergo this transition where you have two states. Let's look at these two states. I have x61 moving along the arc of an ellipse right here, and then it jumps discontinually to becoming a stationary point. But it's doing this ever so briefly, while O is exterior to the circumcircle. There you go. Right now it's going to jump there, and now Mathematica has gone through a divide by zero phenomenon. Let's see if we can exit this and go back to a working animation. I don't know why this is happening, but it is sometimes happening. So as you move center of inversion to the left, you go from a stationary point to a combination of ellipse and a stationary point, elliptic arc and stationary point, to, as you're seeing here, right, I have this elliptic arc and the stationary point, to the mirror image, if I can get to it, but it doesn't look like Mathematica wants to let me do it, to the mirror image, which is just a stationary point. Yeah, so this is happening because we got into a numerical instability here when O is exactly on the circumcircle, and it doesn't look like Mathematica is going to let me out of this. So let me just say this to finish this video. You got the same phenomenon with x62 in that you can have these three states, just a point plus an elliptic arc, or just an ellipse. Okay, so I'll see you on the next video.